Here we are in section 7-2, exercises 7 through 15. Here we're instructed to simplify each expression. And that means, in this case, we have square roots. We need to take out perfect squares. Cube roots, we'll need to take out perfect cubes. Fifth roots, we'll need to take out perfect fifths. So the best way to do that is to write these in factored form with their sets of 2 or 3 or 4 or 5 to identify clearly perfect fifths and perfect squares and perfect cubes. So let's do that. So 50, if we do the prime factorization of 50, we get let's write this out like this. Square root of that's 2 times 25, which is 5 times 5. And that's a perfect square right there. We can see that 5 times 5. And then we'll do this. X to the fifth is x perfect square, and there's one left over. And then y cubed is y perfect square, and one left over. Okay, so what can we take out? We can take out that guy. That becomes a 5. We can take out an x and another x. So we can take out 2 x's. That makes an x squared out front. And then we can take out this one, which is a y. So that comes out perfectly. Those are the perfect squares. The 5, the x, and the y. What's left in is a 2. This x does not have a perfect square in it, and that y is left in there. So there is the simplified expression. All right. Next one, number 8. Let's write this out. This is the square root of 3 times 9, which is 3 times 3. So that's its prime factorization. And one of these, a set of 2, will be able to come out underneath the square root. M to the 8th. Some of you are able to see this. 8 halves power is just 4, but we'll write it out in slow motion. So we have a perfect square, a perfect square, a perfect square, up until we get to 8 of them. There we go. And then on the t's, we get a t perfect square, that's 4, 5, 6, 7. So that's the one that'll be left over that can't come out. So what does come out? We have a set of 2 3's that'll come out. 1, 2, 3, 4 m. So we get an m to the 4th power. Yeah, and some of you can see that. The square root of m to the 8th. Well, what times itself gives you m to the 8th, m to the 4th. And this is how it does it in slow motion. There's a perfect square, comes out as an m. That m squared, square root of m squared is m squared, square root of m squared, 4 times. And then 1, 2, 3 of those sets of t come out. And there we go. And then that 3 has to stay in, and that t has to stay in. So 3 m to the 4th t. Good. Number 9. Okay, 48, t to the 9th, v to the 6th. So let's write this out. This is 2. Let's write that big square root there. 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3, and that's as far as it goes. And then t to the 9th has a t squared, a t squared, a t squared. That's 2, 4, 6, 8. One left over. And then v to the 6th is v squared, v squared, v squared. I still didn't make it long enough. So sets that can come out. That comes out as a 2. That comes out as a 2. So we get a 4 out front. And then we have 1, 2, 3, 4 t's. Timesing together out there, not t squared. That's a t to the 4th out front. And that t is left in. And then a perfect square, perfect square, perfect square. V times v times v is v cubed. And then what are we left with? That 3 and that t, it looks like 3t. Excellent. All right, number 10. Cube root. So this time we've got to do sets of 3. We've got to have perfect cubes in order to be simplified. So when we break down 54, that is, let me see, 2 times 27, which is 2 times 3. 3 times 9 is 3 times 3. There we go. So break down the prime factorization of 54, and you should get 2 times 3 times 3 times 3. Then this one, remember we're doing perfect cubes. And let me see, 3, 6, there's 7 of them. And then y cubed, y cubed, y cubed, and y cubed, and that gives us 12. Again, we break them up into sections of perfect cubes so that we can see them come out. Oh, I didn't draw the 3 right there. So we're looking for sets of 3. That set of 3 comes out, so we got a 3 out front, and then we got that set of 3 x's and that set of 3 x's. Each one comes out as an x, so we get that twice, and then we get 1, 2, 3, 4 y's that come out. So the cube root of y cubed is y. Cube root of y cubed is y. And so you can kind of see this. This is, in fractional exponents, that would be y to the 12 thirds, which gives us y to the 4th. This would be x to the 7 thirds. Let's write that up here just so you can see it happen. If you were to put this as a mixed number, 3 goes into 7 2 full times with 1 remainder. And that's the one that's stuck underneath the radical. So the cube root of, we have a 2 here and an x there. And is that all we have? Looks like that's all we've got there. Good. Number 11. All right, cube root again. So this is, we're going to do the cube root of 2 times 20, which is 2 times 10, which is 2 times 5. And then we've got m, we're looking for perfect cubes. We have 1 left over. So there's your m to the 4th broken up with a perfect cube taken out. And then y to the 16th. So that's a y to the 3rd. You notice we'll get 5 sets of 3 and then 1 left over. And that's just 16 divided by 3. So you get y cubed, that's 9, 12, 15, 1 left over. All right, let's see what happens. This is a set of 3, comes out as a 2. That's a set of 3, comes out as an m. And then 1, 2, 3, 4, 5 sets of y cubed. And what are we left with on the inside? Cube root of, let me see, 5 stays in there, and an m stays in there, and a y stays in there. And yeah, we can look at this. 4 thirds is the same as m to the 1. Here's a full power of m, and m to the 1/3. That tells you it's still in the radical. And y to the 16 thirds, watch that happen. 16 thirds. That's like y to the 5 and 1/3. And so y to the 5th is out here, and y to the 1/3 stays underneath the radical. I don't know if that helps you, but that may see how these fractional exponents give a little insight into how to simplify radicals. All right, number 12. Ooh, this looks big. 7th root. So we are looking for perfect sevenths. That's what comes out of a 7th root. Perfect fifths don't work, perfect cubes don't work, perfect squares don't work. We have to look at sets of 7. Some of you may recognize 128 is indeed 2 to the 7th power. That's 2 times 2 times 2 times 2 times 2 times 2 times 2, right? 1, 2, 3, 4, 5, 6, 7. Yes. So that's the prime factorization of 128. U to the 14th. Again, we're interested. We start with, is there a perfect 7th in there? Yeah, u to the 7th and u to the 7th. And then y to the 23rd. We're going to have a y to the 7th, y to the 7th. It's 14, 21, and we have 2 left over. Okay, let's do it. Here's a perfect set of 7. So that guy comes out as a 2. U to the 7th. 7th root is a u. U to the 7th, 7th root, that's another u. So we get a u squared out here. And then that becomes a y times a y times a y. So that's y cubed. And what are we left with? 7th root of, all the numbers came out. Just a y squared, I think. Yeah, I think that's correct. There we go. Now let's look and see how the fractional exponents help us see what's going on here. This is u to the 14 sevenths, and that just simplifies to u squared, and that's what came out. Y to the 23 sevenths, so 23 sevenths, if you put that into a mixed number, 7 goes into 23 3 times, and that's really what's going on. This is y to the 3 and 2/7. So here's the y cubed, and here's the 2/7 power still remaining. All right, let's do number 13. We're looking for perfect fourths now. So let's do the fourth root of 80. So this is 2 times 40, which is 2 times 20, which is 2 times 10, which is 2 times 5. All right, so there's the prime factorization of 80. Then we have a t to the fourth, and we only have 3 left over. And then y to the 12th, we're looking for perfect fourths. So we take out the first 4, the next 4, that's 8, 12. Oh yeah, this one comes out nice. 12 divided by 4 is going to give us 3. All right, so perfect sets of 4, that's a 2 that comes out. Perfect set of 4, there's a t. And perfect set of 4, perfect set of 4, perfect set of 4, that's going to be a y cubed. Fourth root of what doesn't come out nicely? Fourth root of 5 doesn't come out nicely. Fourth root of t cubed, not enough t's there. And that's it. That's all we have there. Good. Number 14. Fifth root. Now we've got to do perfect fifths. So 96, let's break that guy down. Fifth root of 96, which is 2 times 48, which is 2 times 24, which is 2 times 12, which is 2 times 6, which is 2 times 3. Whew. X to the 7th means we've got x to the 5th and an x squared. And then y to the 12th, we have a y to the 5th, a y to the 5th, and a y squared. Okay, so perfect fifth right there comes out as a 2. X to the 5th comes out as an x. And y to the 5th come out. Each one is a y, so we get a y squared out front. Let's write that a little nicer. And then we're left with the fifth root of 3, x squared, and y squared. All righty. Now notice this. 7 divided by 5 is 1 remainder 2. And there's our full power of 1 and remainder 2. 12 fifths. 12 divided by 5 is 2 remainder 2. And you'll notice these remainders stay as a 2 fifths. All righty. And number 15. We got to do perfect fourths. All right, so let's write that out. Notice it's going to be different than this. With the fifth root of 96, we still get the same prime factorization we had in number 14. We get 2 times 2 times 2 times 2 times 2 times 3, but we're actually only interested in sets of 4. So in this case, we're not going to break this up into sets of 5, but sets of 4, and then 1 left over. And z to the 12th is z to the 4th, z to the 4th, z to the 4th. So this set of 4 comes out. 4 through to 2 to the 4th is a 2. W, that's going to give us a w squared. And then z, z, z. That's a z cubed. And we're left with a fourth root. This is times z. Fourth root of 2 times 3 is 6. W. And yeah, that's what it ends up. Now look at how fractional exponents help us. 9 fourths, 9 divided by 4 is 2 remainder 1. 2 and 1 remains. And 12 divided by 4 is just a straight 3. Excellent.